Our last presenter, oral presenter for today, is Julio Cesar Mendoza Bobadilla, coming from University of Campinas and also from Peru. Thank you. Can you please come? His presentation is titled Learning Attention Maps for Unsupervised Deep and Camera Motion Estimation in Monocular Videos.
Hi, everyone. I'm going to present part of my doctoral project. This work was developed with the collaboration of the Professor Elio Pedrini from the Laboratory of Visual Informatics at the Institute of Computing at the University of Campinas. So, let's begin with the problem. Unsupervised depth estimation and camera motion estimation have as input a monocular video, and the output is a dense depth map for every frame of the input video, as well as the trajectory of the camera, of the moving camera that recorded that video. So this work is motivated first because the model mimics the human learning of the scene structure. It means that at training, we will learn using bidimensional projections of the world. And at testing or at inference, we just need to look to an image to infer the scene structure. Another important motivation is that this has many applications on autonomous driving, interactive robotics, and it could be also applied in scenarios in which the depth sensors does not perform well. So let's begin with some basic concepts. The first one is perspective projection. So in perspective projection, we learn to map 3D points to an image plane. For example, we have here a big X that is a point in a camera coordinate system, and we can project this point on the image plane, the small x, using the focal distance and the offset of the camera. And these parameters are called the intrinsic parameters of the camera. And this mapping could also represented as matricial operations using homogeneous coordinates, in which we just multiply the coordinate in the camera coordinate system by the intrinsic matrix, and then we downscale by the depth value of that pixel. As well, we could define the inverse mapping. It means the mapping from the image plane to the camera coordinate system of the camera by multiplying the homogeneous coordinate in the image plane by the inverse of the intrinsic matrix. This is upscaling with the depth value at that pixel. Another important concept is the Euclidean transformation between the coordinate systems. In this case, we have a camera, the coordinate systems of camera take in 2 instants of time. So we have, for a point, x, we have a coordinate in the coordinate system of at the position t, that is the red line with the red point. And we can project this coordinate in the coordinate system of the camera x that is represented by the blue line. Using just the position of the camera of the second camera center with respect of the coordinate system of the first camera, as well as the rotations of both camera coordinates axes. Finally, with these two concepts, we can map every point between one frame to another frame, just knowing the intrinsic matrix, the Euclidean transformation, and the depth value of on every position of the image. So a common approach to solve this problem is view synthesis. So in view synthesis, the main objective is to synthesize a view using a source view. For example, here we have a point x in the target frame, and with the mapping explained before, we know the position of that point in a source frame, knowing the depth value at that pixel, as well as the transformation between the two coordinate systems. So the whole system is trained with a biosynthesis loss that will measure the photometric error between the target frame and the source frame. And this error will be measured in the set of coordinates at the image and in a small set of nervy frames. So in this work, we observed two aspects of this kind of biosynthesis approach. The first one is that the error contribution of every pixel in the image is the same. But we observed that it's difficult to estimate the depth in regions with a complex geometric structure. So we proposed the idea to increase the error contribution of that complex regions. And another contribution is about pixels that are occluded in a view. Pixels that are present in a target frame but are not present in other frame. A traditional approach use a hard threshold to determine if one pixel is occluded or not, but we propose to use a probability kind of intuition if a pixel is occluded or not in order to don't lose supervision in occluded regions. So let's take a look of our proposal. To learn, we propose to use an attention map to measure the error contribution in every region. So in the original approach, we had a depth encoder-decoder, and we add an attention decoder that is connected with the depth encoder to produce an output an attention map. And we propose to produce a soft occlusion map that will have the probability of every pixel to belong to an occluded region. This model is trained with a photometric error attending to regions that will attend to regions with a complex structure, and we also have a loss that will measure a loss that we'll use it to train the attention decoder that will measure the attention, will increase the contribution in attention in regions that have a simple geometrical structure. So let's explain or talk about the architecture. Actually, there is a multi-scale architecture, and we have skip connections between the layers of the attention decoder and the layers on the feature maps on the depth encoder. And our method will produce an attention map for every scale of the input. In this case, we work with 4 scales. Let's talk about the losses. Our first proposal was to use to multiply the photometric error at each pixel with an attention map. But when we trained our model, actually, the attention decoder learned to increase the error in simpler regions with a simpler geometric structure. So our attention decoder learns to recognize regions with a simple geometric structure, such as flat regions. And then we train the depth encoder and the depth decoder, the depth encoder-decoder and the post network with the complement of the attention map that will increase the error in complex regions. As well, we use an attention regularizer that will avoid the attention map to have zeros and a depth consistency term. The algorithm is trained in 2 steps at each iteration. In the first step, we will train the depth and post networks, and the second step, the attention decoder. So we use it to evaluate our method. We use the KITTI benchmark suite. And this benchmark has sparse depth maps for every frame, as well as a trajectory. Let's look some results. We used a biosynthesis baseline and compared the performance in depth estimation with our proposal, and we obtained better results in using these error metrics that kind of measure the error at pixel level. And the second is a thresholded accuracy, in which we try to divide regions in which the accuracy is good, is medium, or is bad, and try to measure if our method increases the performance in these subsets of the input. We also have results in camera motion. we tested the view synthesis baseline and compared it with a model considering occlusion and depth consistency, and we had an improvement. And we also compared it with the attention decoder, and the results improved a little bit. So we can also check the results visually, and we obtained better results. Finally, some conclusions. We proved with our tested that the error contribution in regions with complex structure boosts the performance of our base model, as well as the proposed formulation of occlusion allows us to reduce the weight of the regions that are probably not visible without losing supervision in these regions that are occluded. Thank you so much.